Hello everyone, welcome to assignment. Today we have 2015 FDQ 8 contest. We have 25 questions and 75 minutes, so let's begin. So let's look at the first question. A 600 meters wide river flows directly south at 4 meters per second. A small motorboat travels at 5 meters per second in still water and points in such a direction that will travel directly east relative to the land. So here is just a vector analysis problem. First we have boat pointing at VB direction. Minus plus the vector of the water direction is equal to the final velocity. So the velocity of water is 4, velocity of boat is 5. Then add the vector together, we have 3 used by the Pythagorean theorem. 5 squared minus 4 squared is equal to 9, and square root of 9 is equal to 3. And 600 divided by 3 meters per second is 200 seconds, which is D. Let's look at the second question. A car travels directly north on a straight highway at a constant speed of 80 kilometers per hour for a distance of 25 kilometers. The car then continues directly north at a constant speed of 50 kilometers per hour for a distance of 75 more kilometers. The average speed of the car for the entire journey is closest to what? So first, let's draw a diagram. We have 25 kilometers and 75 kilometers, and each have velocity 80 kilometer per hour and 50 kilometer per hour, respectively. Then we know the average distance is total distance divided by the total time. So then we can calculate total distance is 25 plus 75, and total time is equal to 25 over 80 plus 75 over 50. Then we can simplify a little bit, and then we plug into the calculator and see what happens. So let's see what is the result. Result is equal to 55.2 kilometers per hour, so it's 8. Let's look at the third question. The force of friction on an airplane in level flight is given by F equal to kv squared. Where k is some constant, v is the speed of the plane. When the power output of the engine is P naught, the plane is able to fly at speed V naught. The power output of the engine is increased by 100% to 2P naught. The airplane will be able to fly a new speed given by what? So we know the power is equal to force times velocity, and plugging Fv squared, we have P naught is equal to kv cube. Then we know the new P prime is equal to 2P naught, which is equal to 2 times k times v cube. Then we want to find the relationship between the initial velocity and the final velocity, how to compare their capacity. So we know the initial velocity times c, all of them cube, should be equal to 2 times v2, which is the after power change velocity. And we know c is equal to the cube root of 2. And what is the cube root of 2? It is equal to 1.26, which is equal to b. The fourth question. A 2 kilogram box is originally at rest on a horizontal surface with the coefficient of static friction between the box and the surface is μs, and the coefficient of kinetic friction between the box and the surface is 0.9 μs. An external horizontal force of magnitude p is applied to the box. Which of the following is the graph of the acceleration of the box A versus the external force p? So first we can write out F equal to ma, then we know A equal to F over m. Then what is F equal to? F equal to P, which is the force applied, minus the friction force, so P plus mg times mu k. Then A is equal to F over m, which is P over m plus g mu k. Sorry, this is minus sign, we got a plus sign. And then from this equation, we can clearly see that this is a linear form of equation that have a point intersects on the negative side of the y-axis, right? If we write equation, replace a equal to y, then this is in the form of y equal to ax plus b, then b is equal to negative g mu k, and a is equal to 1 over m. So we want to find a slope that have negative intercept. Then a is right, b is not right, c is not right, d and e is not right. So now we can only look at a and c. We know there is a friction force suddenly change. One is moving or one is suddenly moving. So there is a discontinuity there by the different coefficient of friction and the magnitude of the force. So the answer is A. Question number 5. A 470-gram lead ball is launched at a 60-degree angle above the horizontal with initial speed of 100 meters per second directed toward the target on a vertical cliff wall that is 150 meters away, shown in the figure. Ignore the air friction. What distance does the lead ball miss the target when it hits the cliff wall? So first, let's calculate the horizontal and vertical distance. Horizontal distance is 150 times the cosine of 60 degree, and the vertical distance is 150 times sine of 60 degree, and calculate it out. Then we can find out the time of traveling, which is the distance, horizontal distance minus the horizontal velocity, which is equal to 75 divided by 100 times cosine 60 degree, which is 75 over 50, which is 1.5 seconds. Then we know the height of the ball will finally travel is equal to Vt minus 1/2 gt squared, which is 100 times sine of 60, which is the vertical velocity, times time, minus 1/2 times gravitational acceleration, which is 5 times 1.5 squared. Then we will have 100 times the square root of 3 over 2 times 1.5 minus 5 times 1.5 squared. Plugging into a calculator, we get 118.65. Then we just need to minus this by the minus the vertical height by this height. Which we'll get is 11.2, which is closest to E. Okay. Question number 6. Three trolley cars are free to move on a one-dimensional frictionless horizontal track. Car A has a mass of 1.9 kg and initial speed of 1.7 meters per second to the right. Car B has a mass of 1.1 kg and an initial speed of 2.5 meters to the left. Car C has a mass of 1.3 kg and initially at rest. Collisions between the cars A and B are perfectly elastic. Collisions between the cars B and C are perfectly inelastic. What is the velocity of central mass of the system of the three cars after the collision? So first, let's look at these two keywords, very important keywords: central mass, velocity. Velocity of central mass. So because we know this system has no external force, so the momentum conserved. So the velocity of central mass is the same at the beginning and the end. So we don't need to consider all this freaking collisions. All we need to do is calculate the central mass of the initial condition. So we have 1.9 times 1.7 minus 1.1 times 2.5, which is the initial momentum, divided by the total mass, which is 1.9 plus 1.1 plus 1.3. Then what we get for the final initial and final central mass velocity, which is equal to, let's plug in a calculator, 0.11, which is 8. So let's look at this next one. Question number 7. Assume that all collisions are perfectly inelastic. What is the final speed of car C? So car A, B, and C are on a horizontal long frictionless track. The mass of the cars are M, 3M, and 9M. Originally, car B is at rest and 1 meter's mark, and car C is on rest at 2 meter mark. Car A is originally at 0 mark, moving toward car B at a velocity of V0. So this time we do need to consider all the collisions. Because we know the collisions are perfectly inelastic, then we know the initial momentum equal to the final momentum. Then we know mv0 is equal to 3m plus m plus 9m times v. Then we calculate v is equal to 1 over 13 times v0. Then we have 8. 7 is 8. Question number 8. Assuming that all collisions are perfectly elastic, what is the final speed of car C? Well, before it was inelastic, now it's elastic. So we need to consider two separate collisions. In order to calculate the elastic collision, we know the energy and the momentum are both conserved. So we have first momentum is conserved, mv0 equal to mv1. v1 is the final velocity of m1, and v2 is the final velocity of the 3m. Then we know that because there's no external force, the momentum conserved. So the central mass speed of the two car system is the same. Then Then because we know the relative velocity between the two cars at the beginning and the end are also the same. So we can use this equation, V1I minus V2I equal to V2 final minus V1 final. Let's just plug in what is V1 initial is V0. V2 initial is 0. Then V2 final is equal to V2. Vi final is equal to V1. Then we plug this V0 back into our original equation, the momentum conservation equation. Then we get this expression. Then we can simplify a little bit. We have negative 2 mv V2 is equal to 2 mv1. Then we know V2 and V1 are equal and opposite to each other. Then we can know that V0 is equal to 2 times V2. So the car 2, eventually you will have 1/2 of the velocity of the first cart. Then because we know that the second cart is 3 times the mass of the first car, and the third cart is also the 3 times the mass of the second car, and the same equation works for both conditions. So we know first time the velocity is cut in half, second time the velocity also cut in half. If you don't believe, you can just work out the algebra and we see two equations that are exactly the same. Okay, calculate the collision between the second car and the third car. So 1/2 V0 is equal to V2, and 1/2 V2 is equal to V3, the car C's velocity. Then we have V3 is equal to 1/4 of V0, which is equal to B. Okay, so question number 9. A 0.65 kilogram ball moving at 5 meters per second collided with a 0.75 kilogram ball as originally at rest. After the collision, the 0.75 kilogram ball moves off with a speed of 4 meters per second, and the 0.65 kilogram ball moves off at a right angle to the final direction of motion of the 0.75 kilogram ball. What is the final speed of the 0.65 kilogram ball? So here we draw a diagram here, and we have one ball moving to the right, collide with other ball, and the final velocities are perpendicular to each other. And we assume the final velocity of the first ball, 0.65 kilogram ball, is equal to v. And the theta angle of the second ball's angle with the horizontal is equal to theta, and the second ball's first ball's final velocity with horizontal angle is 90 minus theta. And when you can equate the horizontal momentum is conserved, so 0.65 times 5 is equal to 0.75 times 4 times cosine of theta plus 0.65 times v times cosine of 90 minus theta, which is sine theta. And second one, 0.75 times 4 sine theta is the vertical momentum of the second ball, and 0.65 times v times cosine theta, which is sine of 90 minus theta, is the vertical momentum of the first ball. Then we can find out v from the last equation, and we plug this v back into the first equation, and then we can solve for the theta angle. After we solve the theta angle, we can plug it back into the v and solve for v. So now after we know v, let's plug in. We'll get this equation: 0.65 times 5 is equal to 0.65 times 4 cosine theta plus 0.65 times 0.75 times 4 times sine of theta square over 0.65 times cosine theta. 0.65 and 0.65 cancel out. Then we will have this expression. Then we multiply both sides of the equation by cosine theta. We'll have 0.65 times 5 times cosine theta equal to 0.675 times 4 times cosine theta square plus 0.75 times 4 times 1 minus cosine theta square, which is sine square, according to trigonometric identity. Then we can solve for cosine theta. Let's plug something back in. On the right hand side of the equation, we have 0.75 times 4 minus 0.75 times 4 times cosine theta square plus 0.75 times 4 times cosine theta square is equal to 0.65 times 5 times cosine theta. Then we see two expressions cancelled out. Then we divide 0.75 times 4 on both sides. Oh no, we divide 0.65 times 5 on both sides. We have this cosine expression. We can express this, then we can solve for cosine theta. So what is cosine theta equal to? This is equal to 0.92. Then what is theta equal to? We plug in the arc cosine function. We have theta is equal to 22.6 degrees. Then we plug this back into the v function. We have 0.75 times 4 over 0.65 times tangent of 22.6 degree. What is that equal to? Plug into a calculator. We get this 1.92. Okay. Let's look at the next question. Question number 10. Let the change in total kinetic energy in the collision be defined as delta K equal to K final minus K initial, where K final is the total final kinetic energy and K initial is the total initial kinetic energy. Which of the following is true? Let's calculate the initial and final kinetic energy first. First, we have 1/2 mv squared, and second one we also have 1/2 mv squared plus m/2 mc squared of each of the ball. Right. Then we will have, let's plug in our calculator, the initial kinetic energy, which is the first equation we list out, is equal to 8.125, something like that. And the second equation, which is the final kinetic energy, which is equal to, let's plug into our calculator, 7.19, okay, which is smaller than the original kinetic energy, which is an inelastic collision, which means delta K is smaller than 0, which is E, which is the only answer that shows that delta K is smaller than 0. Question number 11. A sphere floats in water with 2/3 of volume of the sphere submerged. The sphere is removed and placed in oil that has a 4/3 of the density of water. If it floats in the oil, what fraction of the sphere will submerge in the oil? First, we can know from the Archimedes principle, the water displaced by the sphere is equal to the mass itself. The mass of the water displaced is equal to mass itself. Then, when it floats into oil, let's also use Archimedes principle. We have 4/3 of the density of water, which is density of oil, times the fraction, which is x, of the volume v, is equal to v as rho, v rho. Then we can equate both equations. We have 2/3 v times rho w is equal to 4/3 of x times v times rho w. Cancel out v, cancel out rho w. We have 8/9 is equal to x. Then we have answer C. Okay. Question number 12. Which of the following statements about the pendulum bob's acceleration is true? A pendulum consists of a small bob of mass m attached to a fixed point by a string of length L. The pendulum bob swings from rest on an initial angle of theta max is smaller than 90 degrees. The first magnitude of acceleration is constant for the motion. That's definitely not true. There are two different forces acting on the pendulum. They are at different directions. They're changing constantly. B. The magnitude of acceleration, lowest point is g. Acceleration of the free fall is also not true. It is possible it can equal to g, but there's no reason it have to be at g, because we know the angle is different. Angle can vary, and so the energy change will be vary, and the speed can vary. So the centripetal force can vary, and g is not constant. See, the magnitude of acceleration is 0 at some point of pendulum swing. That's impossible because the gravitational acceleration is always there. D. The acceleration is always directly toward the center of the circle. That's also not true because there are two different forces acting on an object that points at different directions, which cause a direction that's not to the center of the circle. One of them is, but the force of gravitational acceleration is not. And when we look at E, the acceleration at the bottom of the swing is pointing vertically upward. That is true, because we know the pendulum have to have a centripetal force that's bigger than the acceleration, unless the string will break right at the bottom. So 13. Consider the pendulum bob when it's at the angle theta equal to 1/2 theta on way up. moving upward with v theta max. What is the direction of the acceleration of the vector? Well, first we have two different forces acting on the object. One is straight downwards gravitational acceleration, and one is the tension force. Then we add two vectors together, we have a shape like this. We can erase all the other answers, find the closest shape, which is D, right? So question number 14, calculate the duration of tension in the rope. A 3 meters long massive rod free to rotate horizontally about the center. Two 5 kg point objects are originally located at the ends of the rod. They are free to slide on frictionless rod, and they are kept flying off the rod by a inflexible massless rope that connects the two objects. Originally, the system rotates at 4 radius per second. Assume the system is completely frictionless and ignore any concerns about instability of the system. So first, let's draw a diagram. We have two masses connected by a rope, rotate about the center in angular speed of 4 radius per second. Now, what is the tension in the spring? Well, we know the tension is equal to centripetal force of one of the object, because tension force is the one that's acting as the centripetal force. We cannot use two of the mass because tension grabs one of them. If you use two of the mass, it will be doubled. So we use m omega squared times r equal to 5 times 4 squared times 1.5, which is equal to, let's plug into a calculator, 120, which is C, 120. Question number 15. The rope is slowly tightened by a small massless rope motor attached to one of the objects. It is done in such a way so as to pull the two objects closer to the center of the rotating rod. How much work is done by the motor is in pulling the two objects from the ends of the rod until they are each 0.5 meters from the center of rotation. So we know the work done is equal to the change in kinetic energy. So by calculating the initial and final kinetic energy and find their difference, you can calculate the work. So what is the initial kinetic energy? Well, first let's use angular momentum, conservation of angular momentum, to find the angular velocity of the final angular velocity. We have two mass. The moment inertia is equal to 2mr1 squared times omega 1 to 2mr2 squared times omega 2. Cancel out m, cancel out 2. We have omega 2 is equal to omega 1 times r1 squared over r2 squared. Then we calculate this in the calculator. The result we get is 36 radians per second. So now we know our omega 2. Let's plug into our changing kinetic energy, which is 1/2 I omega 1 squared minus 1/2 I2 omega 2 squared. Right? And you need the absolute sign for that. If 1/2 times 2 mr1 squared, 2 mr1 squared times omega 1 squared minus 1/2 times 2 m omega 2 squared times r2 squared. We plug it into the calculator. We get the answer is 1440, which is D. Okay. So now let's look at question number 16. Show below a graph of potential energy as a function of position for a 0.5 kilogram object. Which of the following statement is not true? The range 0 is more than x more than 6. Not true, remember. So A, the object could be at equilibrium, either at x equal to 1 cm or x equal to 3 cm. We know the changing potential energy. Changing energy is the same. Is constant. The derivative is constant at the position 0 at the position. So the force is 0 because force is equal to d over dt dx. B, the minimum possible total energy of object is negative 10 J, which is true. You can see. C, the magnitude of the force on the object as 4 cm is approximately 1000 newtons. Let's calculate the slope of the point at x equal to 4. We have 10 over 0.01 meters, which is about 1000 newton, which is true. D, if the total energy of the particle is 0 J, then the object will have maximum kinetic energy of 10 J. We know the potential energy plus kinetic energy is equal to 0. So we know the minimum potential energy in this here is negative 10. So maximum kinetic energy have to be 10. E, the magnitude of acceleration of the object at x equal to 2 can be approximately 4 cm per second square. We have the slope of the function, which is equal to the force. Then we know the force is approximately equal to, let's calculate the slope, about this height divided by this length, which is about 1 length and 20 height. So 20 over 0.01 meters, which is about 2000 newtons. Right, 2000 newtons divided by the mass, which is acceleration mass, 0.5 kilogram. Then we have 4000 meters per second square, which is way faster than 4 centimeters per second square. Right, so E is wrong. So the answer is E. Okay, so let's look at the next one. Question number 17. A flywheel can rotate in order to store kinetic energy. The flywheel is a uniform disk made of a material with density rho and tensile strength. This symbol, I forgot what it's called, which is in Pascal, a radius r and a thickness h. The flywheel is rotating at maximum possible angular velocity. It does not break. Which of the following expression correctly gives the maximum kinetic energy per kilogram that can be stored in the flywheel, assuming alpha is a dimensionless constant? So this problem is clearly a dimensional analysis problem. We have rho in dimension, which is m over l squared, well, l cubed to the a power. This symbol, which is in Pascal, I think it's sigma, yeah, sigma in Pascal, which is force over area, which is in this fundamental units. Radius r is equal to L, and thickness h is also equal to L. Okay, and finally we want the result is in the kinetic energy per kilogram. Kinetic energy is m times L square over t square. The units divided by m, the m will cancel out. Right. Here the L cancelled out, so let's rewrite all the equation. Again, we have m over L cubed to the a power times m over L times t squared to the b power times L to the c power times L to the d power, which is equal to L to the 2 power divided by t squared. Then we want to use dimensional analysis to do this. So first we know the mass is cancelled out at the end. So A and B have add together equal to 0, right? And also we know that T have to have a negative 2 at the end. So we know there's only one expression that have T in it, which means B have to be equal to 1. Then A equal to negative 1. Then L is finally equal to 2. To second power, so negative 3a minus b plus c plus d equal to 2. Then we get c plus d have to equal to 0. So we can ignore the length, radius, and the thickness. So finally we get is sigma over rho times dimensionless constant, which is E. Dimensional analysis problem. Yeah. So question number 18. Show below the 3 graphs of the same data. Which of the correcting fundamental relationship between the data points, assuming A and B are non-constants, are constants? Okay. So let's look at the first graph. It could be exponential function, right? Or it could be x to the n power function, or it could be a quadratic function. We don't know. It could be anything. But then we look at the second function. Second function is a logarithm function, but it looks linear. There's only one kind of graph can be linear in a logarithm function, which is exponential expression. Then we can clearly know the answer is D. The third graph is using logarithm on both sides, which smooths out the curvature of the graph. That's a way of. This is an interesting fact for you to know. But then question number 19. A YouTube nanometer consists of uniform diameter cylindrical tube that is bent into a U shape. It's originally filled with water that is density rho W. The total length of the column of water is L. Ignore surface tension and viscosity. Water is displayed slightly so that the side moves up a distance L, x, and the other side lowers the distance x. Find the frequency of oscillations. So let's first draw a little diagram. So imagine there's a water in this tank, U-shaped tank, and it's have a little displacement which causes a little oscillation and back and forth. Then we know from the question we ask is frequency. So the constant unit in front of it have to be 1 over 2 pi, which we don't need to consider B and D anymore. Then because we know by increasing the gravitational acceleration, frequency will increase. So C is also not correct. Then we just need to look at A and D. A and D, one is related to L, one related to density. But recall we have a pendulum. We know the frequency of pendulum doesn't depend on the mass. So intuitively we can know that the frequency of the water doesn't depend on density. So the answer is A. Question number 20. Oil with a density half that water is added to one side of the tube until the total length of the oil is equal to the total length of water. Determine the equilibrium height difference between the two sides. So let's draw water with more density, so it's lower to this. And this side is all oil, and there's a difference in height. Right hand side is oil, left hand side is water. The oil have a height, let's define the height of oil as HO, and which is equal to L. And the height from the bottom is water. Let's define this height as changing L, delta L. Then the water is HW, which is equal to L minus delta L. Is that correct? Then let's calculate in order for this system to be equilibrium, there have to be a pressure have to be the same at the bottom of this U-tube. So we have P1 equal to P2, each created by each side of the fluid. One side is only water, one side is oil and water. Then we have pressure. Let's calculate pressure is equal to, we cancel out G, remember. So HO times PO plus delta L times P rho W, this is rho, not P, is equal to L minus delta L times rho W. Right? Let's calculate the pressure. Then we know the rho O is equal to 1/2 rho W. Rho W is density of water, which is 1/2 to get oil. Then we cancel out rho W. We get 1/2 L plus delta L is equal to L minus delta L. Then we know 2 delta L is equal to 1/2 L. Then delta L is equal to 1/4 L. Okay. So because we know that the delta L is equal to 1/4, but remember we want to know the difference between their height, which is twice the delta L. Because we remove, like we can imagine, we remove delta L from the water to add it to the oil. It's height. So we need to, the difference of height is equal to 2 delta L, which is 1/2 L, which is B. Okay. Question number 21. An object launches vertically upward from the ground with a speed of 50 meters per second, bounce off the ground on the return trip with a coefficient of restitution given by CR equal to -0.9, meaning that immediately after the bounce, the upward speed is 90% of the previous downward speed. The ball continues bouncing like this. What is the total amount of time between when the ball is launched and when it finally comes to rest? Assuming the collision time is 0, the bounce is instantaneous. Treat the problems as ideally classical and ignore any quantum effects, okay? Happen for very small bounces. Right, so here we have the little graph here, and we want to calculate the total time it takes for it to go to 0. Well, some people may say it's infinite, it will never come to rest. But we know infinite sequence can still sum up to 0 in calculus BC, remember? Okay, so we know half the period it takes for the acceleration to decrease the velocity to 0. Then we can use that equation to know that g times t1 over 2 is equal to v1, g times t2 over 2 is equal to v2, g times t3 over 2 is equal to v3. Then v2 is equal to v1 times 0.9, v3 is equal to v1 times 0.9 squared. Then we can calculate v1 plus v2 plus t1 plus t2 plus t3 all the way to infinity, which is equal to 2vi over g. We sum them all up. Sum of from 1 to infinity of 2i divided by g, which is equal to because we can use expression to calculate vi, which is v1 times 0.9 to the I power minus 1. We can calculate that. Then that is not a vi anymore, it's a v1. Okay. Then we can calculate this as 2 times 50. 50 is equal to v1 because v1 is equal to 50 over g. G is equal to 10, so we 2 times 50 over 10 times the sum of 0.9 to the I minus 1 power from as I equal to 1 to infinity. Then we can plug in our geometric series sum equation, which is 1 over 1 minus 0.9, which is 10 times 10 equal to 100, which is equal to B. Okay. Question number 22. A solid ball is released from rest down incline on various inclination angle theta, but through a fixed vertical height h. The coefficient of static and kinetic friction are both equal to mu. Which of the following graphs best represents the total kinetic energy of the ball at the bottom of the incline as a function of the angle of the incline? First, we know that when the ball is not slipping, there's no work done by friction, so A and B have to be wrong because the kinetic energy is constant for a while at the beginning. And also because when we know theta approaches 90 degrees, there's a free fall, so the kinetic energy should return to normal. So E is also not correct. So from C and D, what's the difference? At C there's no discontinuity, but D there's a continuity. And we know that by increasing the theta a little bit, the energy will change, because by increasing the angle, we have more slipping force, and more slipping, there's more friction down. So there should be a little bit decrease, and it's a smooth function. So there shouldn't be a discontinuity there. So it should be C. Question number 23. A 2.0 kg object falls from a rest of a distance of 5 meters onto a 6 kilogram object that is supported by a vertical massless spring with spring constant K equal to 72 newtons per meters. The two objects stick together after collision, which results in a mass spring system oscillation. What is the maximum magnitude of displacement of the 6.0 kg object from its original location before it is struck by the falling object? So first, we can consider this system into two parts. First, we let the object drop, and then they have an inelastic collision with the resting object on the spring, and we calculate the change in kinetic energy and how it contribute to the spring system. Then we know from the conservation of energy, when the block hits the resting block, its velocity is equal to 10 meters per second. And by the inelastic collision, we have conservation of momentum. We can calculate the v prime, which is the velocity of the both block after the collision, is equal to 10 times v m1 divided by m1 plus m2, which is equal to 20 over 11. Wait a second, not 11, 20 over 8. 6 plus 2 is 8, which is equal to 5 over 2, 2.5. Okay. And then we are going to use the conservation of energy to calculate the displacement of the spring. We want to know the spring potential, the energy of the system before the spring is compressed, and the energy of the system after the spring is compressed. They should be equal, right? So E of before is equal to the E final, E after collision, after the compression. So what is the energy of the system before? We first have 1/2 k h squared. H squared is the original compression of the spring by the resting block, plus 1/2 m1 plus m2 squared, v1 squared, v prime squared, right? Which is the kinetic energy of the both mass. And that will equal to the E final, which is equal to 1/2 kh plus x squared, the final compression, total compression, plus the gravitational potential energy of the two objects, which is m1 plus m2 times gx. And then now we're going to solve x. So now it's just all algebra, pretty complicated algebra, you know. So let's spend them out. We have 1/2 kh squared plus 1/2 times 8 times 2.5 squared is equal to 1/2 times k times h squared plus 1/2 k 2 times hx plus 1/2 k x squared plus m1 plus m2 times gx, which is about 8 times 10 times x, which is 80x. Then we can plug in the value. We have 1 half k is equal to 36h squared plus 1 half times 8 times 2.5 squared, which is equal to 4 times 22.5 squared, which is 25, which is equal to, and then they are equal to 1 half k again, 36 times h squared. 1 half times k is just 36h squared plus 1 half and 2 cancel out, and khx, which is 72hx plus 1 half kx squared, which is 36x squared plus 80x. Then we can cancel out 36h squared, and then we want to solve for x, but before we need to know what is h. So h is the displacement of the original displacement of the spring by the resting block. So we can use Newton's second law. M1g is equal to kh. So h is equal to m1g over k, which is equal to, let's plug in calculator, 0.83, about 0.83. So let's plug in 0.83 into the original equation. We have 0.83 times 72 plus 36x squared plus 80x, which is equal to 25. Okay. Then we can try to solve the equation. Use quadratic formula to solve the equation. With negative 80 plus or minus 80 squared plus 4 times 36 times 35, all of them over 160, which is equal to x. Then just plug in calculator. This is a pretty long calculation. Then plug in calculator, calculate, and so we got x equal to 1.16, which is closest to b, 1.1. So let's know the next question. Question number 24. The speed of a transverse wave on the long cylindrical steel string is given by this equation, where T is the tension in the string, M equal to mass, and L is the length of the string. Ignore any string stiffness, assume it does not stretch when tightened. Consider two steel strings of the same length when the first radius 1 and second thicker string with radius R2 equal to 4 R1. Each string is tightened to a maximum possible tension without breaking, with the ratio F1 over F2 of the fundamental frequency of vibration of the two strings. Well, first we know that in this equation, the changing variable is the radius, and in the original variable there's no radius change, so probably it doesn't affect at all. So maybe you can choose A. But remember, the mass also matters. But by changing the radius, we change the mass. But also we change the cross-sectional area, which changes the tension, the pressure in the string, tensile strength, or you can say. So the tension and the mass increase by the same proportion according to radius change. So the final result is unchanged. So it's A. So question number 25. Two identical cards A and B, each with mass m, are connected via a spring with spring constant k. Two additional springs identical to the first connect the cards to the fixed points. The cards are free to oscillate under the effect of the spring in dimensional frictionless motion. Under suitable initial conditions, the two cards will oscillate in phase according to this equation, and where XA and XB are the location of cards A and B relative to the respective equilibrium positions. Under other suitable initial conditions, the two cards will oscillate exactly out of phase according to this equation. Determine the weight ratio between their angular frequencies. Let's look at the first case, the in-phase case. The in-phase case, we can consider each of the cards as just being a block oscillating by two strings pulling on each other. So we have two strings with spring constant k and with mass m in between. Then we know the angular frequency is clearly k over m, right? And in all of this case, we have two mass, block A and block B, connected by a spring in between. And because we know the equilibrium position of this spring in between doesn't change, so we can consider as A is occupying half the spring and B is occupying another half the spring. And we know by cutting the spring in half, we double the spring constant. So we can calculate as 2k plus k divided by m, which is the second frequency. Oh, and the first one, we need to double the k and double the m because we consider two cards as one object and we consider two strings. So now we can calculate the ratio, which is in this expression, cancel out all the k and m's, we have square root of 3. So the answer is 8. Okay, so thank you for watching, and thank you for the American Physics Teacher Association produced the solution manual which we referenced, and good luck on the exam.